Magnetic field induction due to a straight conductor carrying current. So in the diagram we have a straight conductor XY and P be a point at a perpendicular distance A. This is the perpendicular distance. A be the perpendicular distance of the point P from a straight conductor XY. O is a point of a small element AC, and this small element is called current element. This small element AC, and the straight conductor is XY, through which a current I is flowing from X to Y, and we can denote the oblique distance R of the point P from the point O of the current element AC. R is the oblique distance of the point P from the point O of the small elementary portion AC or current element. The current element AC has the length dl. Vector dl acts from A to C, and this elementary portion AC is also known as current element, and a current I flows from the end X to Y, and the perpendicular from the point P on the conductor is PD. PD is the perpendicular and A is the perpendicular distance. Small a is the perpendicular distance of the point P from the conductor. We can draw a tangent OT at O on the current element AC, and this tangent OT gives the direction of current at the point O on the current element. And this tangent OT makes an angle theta with the oblique distance r. Theta is the angle subtended by the tangent OT with the oblique distance r. And here the tangent OT indicates the direction of current at the point O. And it is also the direction of current element I vector dl. We can connect Y and P. We can connect Y and P. And also we can connect X and P. Also we can connect X and P. We can connect X and P in this way. Angle subtended by the oblique distance r with the perpendicular distance A is phi. This angle is phi. The end y, or the oblique distance of the end y from the point P makes an angle phi 2 in clockwise direction. The oblique distance of the end y from the point P makes an angle phi 2. This angle is phi 2. This angle is phi 2, and this angle phi 2 is measured in clockwise direction, and this angle is known as positive actually. So this angle is phi 2, phi 2. And also the oblique distance of the index of the conductor from the point P makes an angle phi 1 with the perpendicular distance A, and phi 1 is measured in anti-clockwise direction. Phi 1 is measured in anti-clockwise direction and phi 2 is measured in clockwise direction. And we have to find magnetic field induction at P. Let A, small a, be the perpendicular distance. Small a be the perpendicular distance be the perpendicular distance of the point P from the straight conductor XY, from the straight conductor from a straight conductor XY carrying current I. Straight conductor XY carrying current I. Carrying current I. And we have to find the magnetic field induction, that is B equal question mark at the point P due to the current carrying conductor XY. Now we have to explain what is R. Also, R is the oblique distance. R is the oblique distance of the point P from the point O of the current element or the elementary portion AC of the straight conductor XY. R is the oblique distance. R is the oblique distance such that R is equal OP of the point P of the same point P of the same point P from the point O of the current element, from the point O of the current element I vector dl, from a current element I vector dl or elementary portion AC or small part AC of the conductor, straight conductor XY. Elementary portion AC. R is the oblique distance of the same point P from the current element, and that current element is denoted by I vector dl or elementary portion AC of length dl of the straight conductor XY. Straight conductor XY. Theta is the angle. Theta is the angle subtended by the tangent to OT, subtended by the tangent OT, subtended by the tangent OT at O of the current element I vector dl or AC. Theta is the angle subtended by the tangent OT on the current element OT at the point O on the current element I vector dl with the oblique distance R. With the oblique distance R. In this case, in the diagram, we can describe the diagram. A is the perpendicular distance of the point P from the straight conductor XY carrying current I. Straight conductor XY carrying current I. R is the oblique distance of the point P from the current element AC. R is the oblique distance of the point P from the current element AC or elementary portion AC, and this current element is denoted by I vector dl. Vector dl is the length vector of this elementary portion AC of the straight conductor XY. Theta is the angle subtended by the tangent OT We can draw a tangent OT at the point O on the current element. That tangent OT makes an angle theta with the oblique distance r. Makes an angle theta with the oblique distance r. Now, according to Biot Savart law, according to Biot Savart law, Biot Savart's law, the magnetic field induction or magnetic flux density, magnetic field induction or magnetic flux density at the point P, at the point P, due to the current element I vector dl or the elementary portion AC of the straight conductor XY carrying current I, due to the current element I vector dl or the elementary portion AC is given by dB equal dB. B is the magnetic field induction and dB is what small amount of magnetic field induction. We can draw the diagram again. OB the point of the current element AC, dl is the length of this current element, I is the current which is flowing from the end x to y of the straight conductor, r is the oblique distance of the point P, and we have to find magnetic field induction, that is dB equal question mark at P due to the current element I vector dl. dB equal, according to Biot Savart's law, mu 0 by 4 pi I dl sin theta whole divided by r square. I dl sin theta whole divided by r square. And this will be the equation 1. This will be the equation 1. Equation 1, dB equal mu 0 by 4 pi I dl sin theta divided by r square. Now we can find the expression of theta, r and l in terms of perpendicular distance a and the angle phi subtended by oblique distance with the perpendicular distance. We can denote the distance of the point O of the current element AC from the point D, that is L. L is the distance of the point O from D. In right angle triangle PDO, in right angle triangle PDO, theta plus phi, phi is the angle subtended by the oblique distance r with the perpendicular distance a. Theta plus phi plus angle PDO, which is 90 degree, equal 180 degree. Sum of three angles of a triangle is 180 degree. Therefore, theta plus phi plus 90 degree equal 180 degree. Therefore, theta equal 90 degree. Therefore, theta equal 90 degree minus phi. Theta is the angle subtended by the tangent OT at the point O with the oblique distance r. We get theta as 90 degree minus phi, which is equation 2. Which is equation 2. Again, tan phi from the same triangle, tan phi equal perpendicular by base. So here PD is the perpendicular and base is OD. If we consider the angle phi, then tan phi equal OD is the perpendicular and PD is the base. OD by PD. OD by PD. Now OD is L, small l, and PD is A, perpendicular distance A. A is the perpendicular distance. So here we can write tan phi equal OD by PD equal L by A. L by A, small l, L by A. For tan phi equal L by A, or tan phi equal L by A. Therefore L equal A tan phi. So if we differentiate both sides with respect to phi, then we get dd phi of L, dd phi of L equal dd phi of A tan phi, dd phi of A tan phi equal A is perpendicular distance which is constant. We can bring A outside dd phi. A dd phi tan phi. And here left hand side dl by d phi can be written, or dl by d phi, dl by d phi, or dl by d phi equal a sec square phi, because dd phi of tan phi is sec square phi. Therefore dl equal, therefore dl equal a sec square phi d phi, a sec square phi d phi. Equation 3, dl equal a sec square phi d phi. dl equal a sec square phi d phi. Then we have to find, express r in terms of a. We have to express r in terms of a. Again, cos phi from the same triangle, cos phi equal base by hypotenuse. Base is PD by OP. Hypotenuse is OP, which is A by R. So now we have to find the expression of R. Therefore, so cos phi equal A by R. Therefore, R equal A sec phi. R equal A sec phi. So this is the expression of R, that is the oblique distance of the point P from the current element AC. R equal A sec phi, which is equation 4. So we get 3 equations, and we can put these 3 equations, that is equation 2, 3, 4 in equation 1 to find dV. Putting these values from the equation 2, 3, 4 in equation 1, putting these values of the equations, putting the values of theta, comma, dl and r from equations 2, 3, 4, from equations 2, 3, 4 and 4, we get in equation 1. So putting the values of theta, dl, r from the equation 2, 3, 4 and 2, 3 and 4 in equation 1, we get equation 1 was dv equal mu 0 by 4 pi ideal sine theta divided by r square equal mu 0 by 4 pi I. In place of dl, what we can write, dl is a sec square phi, a sec square phi phi sine, in place of theta we can write 90 degree minus phi, sine 90 degree minus phi, whole divided by, now we know that r equal a sec phi, so under bracket a sec phi bracket closed whole square, a sec phi bracket closed whole square. Therefore dB equal mu 0 by 4 pi I by a, current by perpendicular distance, cos phi d phi. Therefore dB equal mu 0 by 4 pi I by a cos phi d phi. Equation 5. dB equal mu 0 by 4 pi I by a cos phi d phi. So this is the magnetic field induction at the point P due to the current element I vector dl of the straight conductor xy. Now the total magnetic field induction, that is magnetic flux density. The total magnetic field induction, that is magnetic flux density, that is magnetic flux density. Magnetic flux divided by area is known as magnetic flux density, or it is equivalent to magnetic field induction at P due to the whole conductor or entire conductor xy, due to the whole conductor or straight conductor xy is given by B equal integration dB minus phi 1 to phi 2, integration dB minus phi 1 to phi 2. Here important thing is lower limit is taken as negative, that is minus phi 1, but upper limit is plus phi 2. B equal integration minus phi 1 to phi 2 dB. Now we can draw the diagram again to explain the direction of phi 1 and phi 2. This is the straight conductor xy carrying current I. This is the straight conductor carrying current I. P is the point at a perpendicular distance A from the straight conductor xy carrying current I. I is the current which is flowing through the straight conductor xy. We can connect the end y up to the point P, and the oblique distance makes an angle phi 2 in clockwise direction with the end y. Oblique distance of the end y from the point P with the perpendicular distance AC is phi 2. Phi 2 is measured in clockwise direction, and the oblique distance XP makes an angle phi 1 in anti-clockwise direction with the perpendicular distance A. Now phi 2, the angle phi 2 is measured in clockwise direction, that's why this angle phi 2 or upper limit is taken as positive, but phi 1 is measured in anti-clockwise direction, that's why phi 1 means this lower limit is taken as negative. So phi 2 is taken as positive, that is plus phi 2, but phi 1 is measured in anti-clockwise direction, means in the opposite direction, that's why phi 1 is minus phi 1. So in the integration, phi 1 is negative minus phi 1, but upper limit phi 2 is only phi 2, that means plus phi 2. Integration minus phi 1 to phi 2 mu 0 by 4 pi I by A is a perpendicular distance, I by A cos phi d phi. Mu 0 by 4 pi and I by A are constant. We can bring mu 0 by 4 pi and I by A outside integration. Mu 0 by 4 pi I by A integration cos phi d phi minus phi 1 to phi 2 equal mu 0 by 4 pi I by A. If we integrate cos phi d phi, integration cos phi d phi is sin phi only. Third bracket closed minus phi 1 2 plus phi 2 equal mu 0 by 4 pi I by A sin phi 2, putting upper limit and lower limit, sin phi 2 minus sin under bracket minus phi 1, bracket closed, third bracket closed. So we know that sin minus phi 1 is minus sin phi 1. So that's why finally we get B equal mu 0 by 4 pi I by A sin phi 2 plus sin phi 1, bracket closed. So this is the final expression of magnetic field induction at a point P due to a straight conductor XY carrying current I. B equal mu 0 by 4 pi I by A sin phi 2 plus sin phi 1. So this is magnetic field induction, that is magnetic flux density. Magnetic field induction, that is magnetic flux density. Magnetic flux density. At the point P at a perpendicular distance A, magnetic field induction, that is magnetic flux density at the point P at a perpendicular distance A, at a perpendicular distance A from a straight conductor, from a straight conductor from a straight conductor XY carrying current I, carrying current I, carrying a current I. So we get the expression of magnetic field induction B. And according to right hand thumb rule or right hand palm rule, according to right hand thumb rule or right hand palm rule, right hand thumb rule or right hand palm rule, right hand palm rule, this magnetic field induction due to a straight conductor carrying current I, this magnetic field induction or magnetic flux at the point P is perpendicular to the plane, is perpendicular to the plane containing vector dl and vector r, and we can draw the diagram again to explain the direction of magnetic field induction. I is the current which is flowing through the conductor xy, A is the perpendicular distance of the point P from the straight conductor XY. Magnetic field induction vector B acts inwards. That's why under bracket cross sign is denoted. Is perpendicular. The magnetic field induction at P is perpendicular to the plane. Plane means the plane of the green board. Plane containing vector dl means length vector of an elementary portion of the conductor. We can consider the current element AC of length dl. R is the oblique distance of the point P from the current element. The plane containing vector dl and vector r. Containing vector dl and vector r. Vector dl is the length vector of an elementary portion of the straight conductor XY and acts inwards. With respect to the direction of flow of current is flowing upwards. The point P exists on the right hand side or right side. And we know that if the point P exists on the right hand side, magnetic field induction vector B will be acting inwards. Vector B will be acting inwards. Vector B acts inwards, and that's why under bracket of B, cross sign is given.